Hello everybody, my name is René Mayet. I'm going to talk about my topic presentation. It is about graph key, large-scale graph computation on just a PC. This paper is important because it offers the possibility of performing real-world graph computation such as social networks, analysis, protein interaction, or web graph on a single modern PC instead of using a distributed computing cluster. The proposed disk-based system analyzes graphs with billions of edges. GraphKey uses a new method called parallel sliding windows (PSW) to process large graphs from disk. Furthermore, it is able to perform data mining, graph mining, and machine learning on large graphs. Additionally, the proposed system performs well on SSDs and hard drives. Finally, the authors decided to develop this project due to the complexity and expensiveness of distributed computing. The state-of-the-art at the moment of this paper was represented by running GraphKey on an Apple Mac with dual-core 2.5 GHz Intel i5, 8 GB of RAM, 256 GB of SSD, and a 750 GB hard drive. Furthermore, there was no other single PC system for large graphs reasonable performing. We are talking about 2012. However, at this time, recently, there are two other systems that claim to outperform GraphKey. That means TurboGrafx 2012 and GraphQ 2015. TurboGrafx and GraphQ are not part of this presentation. However, they are mentioned because they claim to be better than GraphKey. So it is to do a complete study is useful to present also the products that at this time, the papers that at this time perform better than the paper studied as the main matter. However, these two papers, TurboGrafx and GraphQ, are referenced at the end. The main methods of this paper and the result are as follows. The new method introduced in this paper is called parallel sliding windows, PSW, to process large graphs from disk. It works by processing a graph with mutable edge values efficiently from disk with a small number of non-sequential disk accesses. The process is done in 3 steps. In the first step, it loads a subgraph from disk. In the second step, it updates the vertices and edges. And finally, in the third step, it writes the updated values to disk. In the graph, we see how the vertices of a graph are divided into P intervals. We have interval 1, interval 2, until interval P, shard 1, shard 2, until shard P. Therefore, under the PSW method, the vertices of a graph are split into P intervals. For each interval, we associate a shard, which stores all the edges that have destination in the interval. Edges are stored in the order of their source. Intervals are chosen to balance the number of edges in each shard. The number of intervals P is chosen so that any one shard can be loaded completely into memory. Similar data layout for sparse graphs was used previously. For example, PSW does graph computation in execution intervals by processing vertices one interval at a time. To create a subgraph for the vertices in interval P, their edges must be located from disk. First shard P, which contains the in edges for the vertices in interval P, is loaded fully into memory. We call those shard P the memory shard. Second, because the edges are ordered by their source, the out edges for the vertices are stored in consecutive chunks in the other shards, requiring additional P-1 block reads. Importantly, edges for intervals P plus 1 are stored immediately after the edges for interval P. Intuitively, when PSW moves from an interval to the next, it slides a window over each of the shards. We call the other shards the sliding shards. Note that if the degree distribution of a graph is not uniform, the window length is variable. In total, PSW requires only P sequential disk reads to process each interval. A high-level illustration of the process is given in Figure 2 and the pseudocode. As shown, this is the algorithm of the parallel sliding windows. This algorithm is an iteration. That means that it is repeated for each shard. So it starts with the first shard and it ends with the P shard in an interaction. As claimed by the authors of this paper, GraphQL can be used for machine learning, data mining, and social networks analysis, which are the topic of our project. On the other hand, GraphQL runs on a single PC, which gives the possibility of performing low-cost research. Furthermore, the paper uses sparse techniques, which are also used in our project. Concluding, the paper is a good introduction to large graph analysis on a single PC, but it seems to be overperformed by TurboGrafh and GraphQL. GraphQL can also solve large problems for distributed systems, but with a fraction of the resources. So, even if this system is slower than the cluster systems, it is cheaper. So that's an advantage in particular cases. In the references, we have, of course, first our main paper, the GraphQL large-scale graph computation on just a PC. And then we have the other two papers that I found regarding an evolution of GraphQL. So systems that overcome GraphQL. One is TurboGrafx, a fast parallel graph engine handling billion-scale graphs on a single PC. And the other one is GraphQL, graph query processing with abstraction, refinement, scalable and programmable analytics over very large graphs on a single PC. These two papers are just cited as a reference to see the state of the art at this time. So, it seems that there are better systems. However, GraphQL is a starting point, even if there are better systems. There is also a website to download GraphQL. As you can see on this website, which is reference, you can download GraphQL, the open source project. There is a version in C++ of GraphQL, and there is another version of GraphQL in Java. It could be a good idea to download it to make evaluations